Today we will be simulating airfoil case with row central foam, like how sir explained. Meanwhile, I'll also start downloading and follow along. Okay, you can just paste it anywhere as of now. Now I will tell you what folders to extract and paste it in your run directory. So after you download, you would see something like this: nozzle hypher some number .zip. So first we will extract using WinRAR. So I will extract using WinRAR and extract to and extract files, extract here. Three options will be there. You press extract here. So after you do that, you will get a folder called nozzle. You open that. Inside that, you will be finding three files. So one a folder and two files. So this is a video which you can look at. So that is a spoken tutorial made much before. It is made in Ubuntu. So if you want to know how the block mesh is made, how all the boundary conditions are set, you can watch the video later. But if you just want to look at the presentation which they used in the video, you can open and see the PDF file which is there. Or else, if you just want to follow along with me, then we will proceed from here. So after you get into the folder called case files, you will find something called nozzle folder. So inside the nozzle folder, we will have the main working files, right? So what you have to do is just copy the nozzle folder and open your terminal. After you open your terminal, uh, we can start to create a folder for this exact case. Okay, first I will go to the run directory. Your terminal will look something like this. Okay, now we will open Explorer at this place inside the run directory, and we will paste the nozzle folder which we just copied in the run directory. So once you have pasted the nozzle folder in your run directory, then all we have to do is stay in the terminal and we should not change the directory at all. So we can do everything within this run directory. So first we will enter the nozzle folder using cd nozzle. So after you do this, there is absolutely no need of changing any of the directory. So whatever commands I am telling, it will be through this directory. So please do not change your directory, then you will face faults like file not found or folder not found. So first we will see what are the folders which is there in this folder. So we will be having 0, constant and system. So this is the exact location where we will be running all our simulation. So the 0 is the initial boundary conditions file, which will have all the 0th time step files. Then there is constant and there is system. First, let's see what is there inside 0. So I will open everything using Notepad for your convenience. If you are using Ubuntu, you can feel free to open it with gedit. But for WSL users, it will be much easy to open with Notepad. So once I can see that I have a folder named 0, but I cannot see what is there inside 0. So what I can do is I will type 0 slash, and if I press tab once or twice, it will show me what are the files which is there inside 0. So I can open something very specific. Now in this case, I'm just going to open velocity file. Okay. Inside the velocity file, we can see there is inlet, outlet, nozzle, back, and front. So there is something new here. You did not see wedge type. So we have seen patches like inlet and outlet, but here we are seeing something, it is just a wedge. So we have to see what is it only while looking at the geometry. Okay, so I will close the notepad. Now I will open the next file, which is the pressure file. Okay. Now when you saw the velocity file, we did not give any inlet velocity. It is given as zero gradient, meaning the solver will calculate the inlet and outlet velocity because we have given as zero gradient. Then how is the flow happening? The flow is happening because of the pressure. So here you can see at the inlet we have given the type as total pressure, the gamma. So gamma is the compressibility ratio, Cp by Cv, specific heats, the ratio of specific heats. For air it is 1.4. So we have defined that, and we are giving the initial inlet value pressure. So that is uniform 10,000, and again the value is 10,000. At the outlet, we are giving a pressure which is less than what is given in the inlet. So we are giving a pressure gradient along the domain. So that is causing the flow. And for nozzle, it is given as zero gradient. Nozzle is the body of the nozzle. So pressure is calculated at that point. And front and back is chosen as wedge. So we have seen empty patches for front and back while doing a 2D case. But what is a wedge? So we will see that after we run block mesh. Before that, we have one more file to look at. So if you do not close your notepad, the terminal will look something like this. So either you can close your notepad or press Ctrl C here. So that will close the notepad on its own. But you can still find the notepad is open, but it is not connected to the terminal anymore. So that is one way of doing, or you can close your notepad. It's up to you. So the last file we have to view in the initial boundary file. So T is temperature file. Again, the front and back is chosen as wedge, nozzle and outlet is chosen as zero gradient, and inlet we are giving a fixed temperature, that is 298 kelvins. So everything here is in Kelvin. As we can see in the dimensions, this will be mass, length and time. So the fourth SI unit or the dimension which we are using is temperature, which is in Kelvin. So the first one is MLT and the fourth one is Kelvin. So that's it about the initial boundary cases. Now we will see the other folders, like the system where our block mesh dict is placed. So we will open that in Notepad. So this is the block mesh dict file. So after you open it, you might not understand anything based on what you have learned about block mesh dict earlier. Just like how we did in the aerodynamic case, this is slightly advanced block mesh where we are giving user-defined code to generate curves. So if you want to understand more, you can look at the PPT, which is or the PDF, which is given along with this files, the one which you downloaded. So here you can see that they have included a function called code include, which is a way of defining user-defined functions. So they are using user-defined code to generate these curves. So these curves will make up the geometry for block mesh. So there are lines, splines, edges. So everything is defined. And then when you scroll down, you can see the normal block mesh structure. So that is defining the inlet, outlet, nozzle, back and front. Here you can see the back and front is defined as wedge. Nozzle is a wall, just as we expect. Inlet and outlet are patches. So that is what we normally do. So that is what is also followed here. There is nothing new in naming the or defining the type of patches or type of boundary, but how the geometry is created is more advanced here. You can try to change some values here and explore it, but if you just want to take the default nozzle, it's not a problem. You can just leave it as such and you can follow along. Okay, the next file inside the system is the control dict, FV scheme and FV solution. We have these three files more. So first I will show you the control dict. So the control dict shows the type of solver which we are going to use. So the application which we will be using in this tutorial is row central form. This is very versatile for such cases. So we are using row central form. The start time will be 0 and the end time will be 0.4 seconds. So this is a transient solver. So we'll be defining the time step as well, which is defined by the delta t. So it is taken as 10 power minus 6. So it is a pretty small time step, and the simulation is going to run for a longer time, relatively longer time than what you did earlier. The right control, these are just default things which you can leave without changing anything. The next file which we have to look at is FV schemes. Okay, as you might have listened to the lecture, we have flux scheme, which is Kurga now here, and I think someone asked in the first hands-on session how we can change the DTT scheme from Lagrangian to Euler. So here are some ways of customizing your schemes, the finite volume schemes which will be used for your solution, and we have also defined other schemes which will be used here. So this is the file which will know, it will tell OpenFOAM, the solver, to choose which scheme we have to use to solve the certain simulation. Okay, so we don't have to look at FE solution, there isn't much, but if you want to explore, you can do it. Now, again, we are in the same directory. We did not change any directory at all. We are in the 0, constant, and system. So before we see the constant, first we will run our block mesh. So okay, now we will start creating the mesh. So the command to start running the mesh is just block mesh as usual. So after you type block mesh with M capital, hit enter. So it will not look like how we generally do. It will look very abstract, something like this, but you need not worry. Just let it run without disturbing, and it will end after some time. Let's wait. Okay, once it is over, you should be seeing something like this. Patch 0 to 5, inlet, outlet, nozzle, back, front, and axis will be created. And then there will be end. Okay, you might wonder that we did not name anything as axis, but we have created a wedge, so axis will be there. Now let's see why it is actually created, and we will view the geometry. So to view the geometry, you can do two things. If you are on an Ubuntu machine, you can directly hit parafoam and view it. But if you are on a WSL, I would recommend you to do touch space uh, nozzle dot foam and hit enter. Then we can open the case at explorer.exe space dot. Make sure that you are doing everything in the nozzle folder itself. You should not change the directory again. So after I hit the enter, the explorer will open. Here we can view the mesh. After we run the block mesh, you can see there is a new folder called dynamic code. You need not worry about it. It is created because of the user-defined code which we have used inside block mesh. So now I will just open ParaView. Okay, after you hit apply on the left panel, you will see something like this. So you might wonder, this does not look like a nozzle at all. We will come about it. This is just one small wedge of a nozzle. So if you can imagine, the nozzle is a circular or say cylindrical kind of revolved geometry, but it is uniform, right? So whatever the flow is happening, it's going to be the same along all the sides. So if we just take a slice of the wedge or a small section, it is going to be same throughout the nozzle. So if we just get the values around here, it is enough. So why are we doing this instead of running the entire geometry? To reduce the number of cells. When you run the simulation, you will know it is taking a lot of time to end the simulation. So as the number of cells increase, as the geometry gets bigger, the time will be taken longer as well. So to reduce or simplify the geometry as much as possible, we are taking only a small wedge of the nozzle and we are viewing the results. It's more like doing a symmetry case. So you might see when you use ANSYS Fluent or something, we will, to take flow over a cylinder, we will just do the upper half and then reflect it to get the other half. So that is exactly what we are doing here, but instead of taking a small slice in the 2D, we are taking a wedge since this is a revolved part. Okay, so this is what we have here. Now we will see the mesh. So this is a very simplified block mesh. As you can see, it is completely hexahedral, and you can see there is no thickness at all. So again, this is a 2D case. Now we will see what are the patches that we have created. There is inlet and outlet. This one is inlet, and here we have the outlet, and we have the nozzle patch which is on the top. This is the wall which we have created. This is the only wall in this domain, and we have front.
Hello.
Yes.
Okay, for this inlet and exit patches, I think
Yeah,
we have used straight line to connect point 1, 2, and 4, 5. Is that correct?
yeah, we have that as axis here.
No, I'm talking about the end points of the patches. Point
Which patch?
0 and point number 4 are on the axis, I
Yeah,
guess.
okay, so that is made for creating a block. After you create the block, we are creating a spline, and the block adheres to the spline and creates a geometry.
No, my question is, can we use arc to create a circle to join point number 1, 2, and 4, 5?
Yeah, you can do that, but it won't be a 2D case. That's the thing.
All right.
Okay. Then we have the front and back patch, which is this one and this one. So that is all about the mesh. If you want to view the entire mesh, you can just select internal mesh and click apply. So this is all we have, and it is in the Z normal. Okay, now we will close this, and we will go to the terminal again, and we will see how we can run the simulation. So before we run the simulation, we have to know certain parameters which we are using, like the temperature and everything. So inside the constant folder, we have one folder and two files. This polymesh is the block mesh which you created. The polymesh folder contains all the information from the block mesh which you have created. And apart from that, we have two files. So one is momentum transport, the other one is thermophysical properties. First, the momentum transport is a very simple file. So it just says the simulation type is laminar. So we are running a laminar case. So that is all about momentum transport. But if we are going to choose something, a turbulent case, then we will be using RAS here and use K epsilon or K omega as palette almiras, like how we did for the airfoil case. But in this case, it is just a laminar. So we will leave it as such. To view what is there in the thermophysical properties, I will open it in Notepad. Now this is the main file which contributes to all the thermal related property inputs. Okay, so we have a function here, thermotype. These parameters are mandatory for any thermophysical properties file. There is a type. So the type which we are using here is HE psi thermo. There are many models or many types which you can be using for thermo type, but in this case we are just sticking on with HE psi thermo. And for mixture, it is a pure mixture. It just contains air. There is no multi components. So we are multi compounds. So we are just defining it as pure mixture. And the transport is constant. Thermo is H constant, naming enthalpy constant. The equation of state is perfect gas. If you can recall what Professor Janani explained, there is also another state called Bosonesque. So there are many states which you can be using. Here we are using perfect gas, and the species is we will just define it as PC. We will come why we are doing that. The energy is sensible internal energy. There are other energy models as well. You can see through the documentation. So in this case, we are using sensible internal energy. And coming to the mixture, this will define all the parameters of the working fluid which we are using. In our case, it is air. So for air, we will be defining the molecular weight, which is 29. Everything is in SI units. So the CP is the specific heat at constant pressure, which is in general we'll be using 1.005, that is kilojoule per kilogram Kelvin, but we will be taking in joule per kilogram Kelvin, hence it is 1005. The HF is enthalpy of formation. So this is generally used for chemical mixtures. where there is a chemical reaction that is taking place. So it is the formulation which will be giving it the heat of fusion or enthalpy of formation. That is what HF is. In this case, we do not have chemical mixing, so we will be defining it as 0. And for transport at very high Reynolds number, it is convenient to treat the case as inviscid. So we are defining mu as 0 by considering the case as inviscid flow. So if you want to define some viscosity, you can proceed and type the value in SI units. So the Prandtl number is taken as 100% efficiency to the viscous and thermal efficiency. So we are taking Prandtl number as 1. This is not a realistic case. If you want to take a real Prandtl number and simulate your case, you can modify the values. So that's it about the thermophysical properties as well. Now I will close this file. Now we are ready to run the simulation. So is everyone okay? How we can solve invisible problems? So I think I just answered it. If we want to define the viscosity, we can define the viscosity over there. The mu, it is dynamic viscosity, by the way. In this case, does the thickness affect the overall solution? So if you mean the thickness of the geometry, it does not affect the results, but it can affect the simulation because it will take a lot of time. It will not affect the overall solution. It is just same. We are just taking one small part of the nozzle, which will be approximately same as all the regions. Okay, then, so I will run the case. So to run the case, all you have to do is type row central foam and it will start running. So I'll hit enter. So it has started, but I am stopping it in between because this is going to take a lot of time. I have already run it for demonstration purpose. So I will show the code alone if you want to run it. Okay, it has gone. So the command is row central foam. I will also put in the chat box. So once you are in this directory, you can hit row central foam after you do the block mesh, and we will be getting the simulation run. So I have run it for our convenience. Now I will show it. After you hit apply, you will see something like this. So the simulation is done, and initially when you load the results, it will be at the 0.05 time step, but the simulation goes up to 0.4. If you let it long enough till the simulation ends, it will go up to 0.4. So I will load it directly. Realistically, you will not be having the result by now because it takes a lot of time. So you just see how I am post processing it to make a complete 2D side of a nozzle. Then you can let the simulation run. After it is over, you can try to visualize. So first, I'm going to the last time step. Either you can choose the time step yourself or press this button and it will go to the latest time step. So it is in the pressure actually. So first, let's start with velocity, and you click on this, it will rescale to the visible data range. So after I hit that, you can see how the velocity actually changes the shock, how it is created. Then you can go to the pressure and hit rescale. Again, you can see how the pressure varies. And similarly for the temperature and the density. So we can view all of these, but it does not seem very convincing when we look at a nozzle only on the half. It's not even a complete 2D, right? So what we have to do is first we will take a slice of the 2D. So to take a slice, you can press on the fourth button here. It will say slice. And by default, it will make a slice on the X normal. So you can choose X, Y, or Z normal here. For now, in this case, the geometry is in XY direction, XY plane. So we have to see the 2D plane through Z normal. So I'll press Z normal and click on apply. So if you want to hide the plane, just check out this show plane thing and the plane will not show. So if you see, we no more have the wedge, we just have a 2D plane. Okay, I will go to the Z normal. Now we have to do something called reflect. So where you can do that is go to sources. On the top, it is the fourth button. To sources, click on search. Then you need not press anything on the screen. So it is not a search bar actually. So after you hit on sources, just hit search and start typing reflect. So after you hit the reflect, first what you can see is when you hit apply, it will by default make a reflection on the x minimum. So this part is x minimum, this is x maximum. So similarly by default it will make a reflection on the x minimum plane. You can change that to y minimum and see how it happens, and this is exactly what we want. Okay, so we are on the y minimum, which is the ordinate, and we are reflecting the entire thing over this plane. So this is our pressure and the velocity and the temperature, and we can also see the density. So you have run the case. That's it for running row central form for a nozzle.
Excuse me,
Yes.
why you are not using an outlet domain for the nozzle?
So we are defining outlet domain as well, but we are not doing that in velocity. Instead of that, we have defined it in the pressure. So that is the only change which we are doing. Let me show you the zero file. So in the velocity, if we see, we are giving the boundaries as zero gradient and in inlet and the outlet. Okay, so the velocity is actually calculated based on the pressure. So we are defining the pressure here. So I'll open the pressure file. Here you can see we at the outlet we have chosen a lesser pressure than at the inlet. So that causes a pressure difference and thus a flow. Can we rotate the wedge to create complete 3D? Not after we run the simulation, we can only do reflection. But if you want to run a 3D case entirely, you can even do that. That's not a problem. But after we run with this type of geometry, the wedge geometry, I don't think we can revolve and make it into a 3D case.
So what I'm asking is, it allows user to create a scalar and define an equation and then plot that property inside the paraview.
Hmm. I searched for revolving the entire thing just like how we have reflect. I thought we would have something in paraview, but unfortunately I couldn't find anything like that. But no, you can use Python, take all these data, and if you can post process them, then of course you can make it. But necessary, right? What is the point in actually making a 2D thing?
I have tried axisymmetric simulation using block mesh dict file and by importing a mesh file from pointwise. But in both the cases, after running 33 milliseconds, the simulation is getting floating point exception.
Okay.
Can you tell me what can be the reason behind this?
Are you using any turbulence models?
No, not a turbulence model because the nozzle throat size is almost 1.5 millimeter. So the flow is in laminar regime.
Okay. So either your mesh is not small enough, if it is a transient case, or your time step is not small enough. So floating point
Is
exception error is the case where the equation is hit by divided by zero case. So it continuously generates decimals and we could not get a finite value. So that is why we are getting floating point exception error. If you look at the residuals, it will just blow up instead of going down. So that is the case why we are getting the exception error. But if you want to solve it, you can try to reduce the mesh size or reduce the time step. You can check with the stability criteria formula.
okay. Thanks.
Okay.
The professor in previous
Yes, yes. Okay.
showed a flow over a wedge or some kind of a ramp,
Yeah.
a
Okay.
deflection. So is it possible to solve similar problem using this solver?
Yes, we can do the exact thing using this solver. All you have to do is replace the mesh made in block
Mhm.
mesh, and you can
Yes.
import any mesh from software like Salome, Gmesh, or even Fluent Mesh. You can import such meshes into OpenFOAM and you can run it. Or else there are other utilities like Snappy Hex Mesh, which is not covered in this workshop. You can use that to generate the mesh inside OpenFOAM itself, just with the geometry. If you have an STL
Yes.
file, you can use that to create a mesh inside OpenFOAM, and you can run some similar cases using row central form. So all you have to
Okay.
do
So,
is set the boundaries properly.
so that's my question actually. The boundary problem will be different from this nozzle
Okay.
problem, right? So
Yeah.
could you,
So
for example, the inlet and outlet and the wall boundary condition, what could we set it for such problems?
yes. So how we can do that is, while we import some geometry or some mesh, take example of Salome. So when you make a mesh, you will be given a choice of making the naming selections. You can recall that from
Right.
answers as well. So after we do the naming selections, let's take case of answers fluent. So after you make the naming selection, you will save the file in a format called .msh. You can import that file here, and you can convert that into OpenFOAM understandable
Yes, this
mesh
I
format.
understand.
So you can do that as well.
My question is what the boundary condition, like what is
Yeah,
the
so
choice of
the same naming is imported here as well. So what you can do is, you know what is the wall, right? So you will be defining wall, everything in similar condition. Like see, in this case, the nozzle is the wall. So if you're importing something related to wall, you will know the namings, right? So you will be defining slip or no slip over there. And if it is inlet and outlet, you will give zero gradient. But if you even are confused with what is the name of the boundaries which you have imported, you can do this. After you import the mesh, you can open the mesh in paraview. Then you can visualize here. You can see, right, the mesh regions. It will give all the namings here. So you can check in, check out, and find what are the mesh regions. You can do that.
uh I
Yeah.
got it.
Okay. So it is very ideal to give namings just after you make a mesh. But if you're using block mesh to make the namings, it can be done as well. While you are creating the block mesh itself, you can give the name, like how we did in this case. We have given the name while making the mesh. And you can also define what type of boundary it is, and we can simulate it.
And we can use the same thing as an empty boundary condition, that the type.
Yes, if you are taking a 2D case and have an extrusion like how we did in the airfoil case, or what we did day before yesterday. So if you want to do something like that, you can take the front and back plane and define it as empty.
Okay.
So all we will have is something like this. It will have only one element here. As you can see, this is just one cuboid on the Z normal. So this is what we consider as a 2D case. So there is only one extrusion. So this is front and back plane, which is defined as empty. Then it will behave as a 2D case. Then you can take the slice and see it. I think someone asked how we took the slice. So I'll do it again. You can see. First, make sure that you have clicked on parafoam or whatever the file.foam you have created. Then you have to press the fourth button. This will show a slice. When you click slice, by default it will be on X normal. So you have to change that to Z normal on the left panel. After you press that, you can check out show plane. It will hide the red color plane which is showing. Then click on apply. Then we will get a slice. I hope it is clear. Yes. Okay. After you get the slice, go to sources on top and give search. In search, you type reflect, hit enter, and in this you can choose the plane on which you have to reflect. For us, this is Y minimum, and click on apply. Then you will get entire nozzle.
Sir, reflect option is showing, but after that, what to do, sir? Means how to select
Uh,
that?
After we load the results, first we will slice. So slice with Z normal plane, hide the plane, and click on apply. After that, you can directly go to filters and show alphabetical. If searching doesn't work for you, click on filters, hover over the word called alphabetical. You will get something like this. Then you can choose reflect if it shows for you. See, so you just press reflect, and before you do that, make sure that you are clicking on slice. So we are reflecting only the slice, right? So after you click make the slice, make sure to press on slice, and then you have to give the reflect. So only then it's going to work. On the after you press reflect, change the plane to Y minimum and click apply. That's it.
Yes, sir, it's done.
Due to display problem in paraphone, I'm just restarted my PC. How can I? Okay, if you lost everything and you don't have a command prompt anymore, just like me, what you have to do is open your command prompt first. After you open your command prompt, you just go to the run directory. There you will be able to find the nozzle folder which you placed. So enter into the nozzle folder using the command cd nozzle. Before that, I'll clear this. Okay, the first command would be cd nozzle from your run directory. Okay, so after entering cd nozzle, you will find all of the cases, like whatever simulation you have run, you will find that there. Then you can open that location in explorer.exe space dot. Then you can load the nozzle.foam or para.foam, whatever you have created, the para view file. So the files will always be there inside the location where you have run the simulation. All you have to do is just open the paraview file, then it will run. So it doesn't matter if you have closed the terminal or not. If you go to the location properly, the case directory properly, then you can run it. Jashwant, I think the problem is you are using 2012, or is it my file? Not sure. No, I think you are using 2012. So if you are using different version, I don't think this might work. Might or might not work.
It is the same problem that we told you previously, right? Between different versions, the functionalities may not be the same. The function name may change, or there may be some major modifications as well.
If you are using OpenFOAM 9, then it will work. Otherwise, there could be errors. Because OpenFOAM 2012 is a different version. It's an ESA version. So it will have its own different name or function. So we have to other by that if we are making case for that one, that version. So I have dropped the link for spoken tutorial 9 and 10. So if anyone got today's tutorial properly, you can try this.
Sir,
Let
actually,
us know.
my velocity display is not showing the same as yours. Means in ParaView, when I use that reflect option and then applied it, but the U
The
magnitude
color is different.
yes, yes.
Okay, if the color is different, then it is a very simple problem. It's not a problem at all. Okay, on this left panel, you can see there is a option called coloring. So it stores specific values. For example, this is the pressure and this is the velocity because I have set this color. But if you want to change the color, you can press on edit. This panel will open up. If you want to see all the color maps which is available, you can select from any of these. The one I'm using is turbo. If you can use that, or you can choose anything, like probably something like this. It's up to you. So anyways, we are just going to infer from the data or from the color map. So you can choose anything you want. I think Akil, the problem you are facing is that you did not press this button. You have to rescale the values to to whatever there is on the screen. So when you press this button, it will rescale all the data to visible range. So whatever is there on your screen, it will rescale to that. Let me tell you one example. So if we see it is all blue here, right? But it will have some variations. So if we isolate only this region and hit this button, it is going to change all the color map value, the range from dark blue to dark red. Whatever data is available on the screen, it will rescale to this thing. So this color map. So that is why we are getting like this. So if you see you are getting a color like this, a dark red, it is because of that. So you just hit this button.
Yeah,
Yes.
actually, my network is down when I'm doing this half an hour back. So I'm facing an error. Shall I share my screen?
Okay. Ideally, this should work, but can you type ls?
Yeah, I checked that too.
So the problem here is that he is running. He
Yeah,
has installed OpenFOAM in root. If you
root
see, his
directory.
installation is in the root directory.
So that
Yeah,
is the
it's in
problem.
root. It's in root.
So you shouldn't do that, because when you're doing installation in root, if you see the error, it is saying that calc function is not enabled, right?
Yes, yes. Yeah, the
So that
same.
calc function, it is not able to call because it is in the root directory. So this was working for everybody else because they installed OpenFOAM in the as a user.
Okay.
So this is the problem.
Okay, sir.
Uh,
So I have to reinstall the version.
Yeah, you can install, but don't install in the root directory. Install in the proper OPT folder. Then this permission error that is there, right? This calc function, see over here, using calc entry at line 20, and there it is saying this could not be executed because because of administrator right, because of security reason. Hmm. So it is because of all those things. So there are complications in that. So I think this problem will be resolved if you run it as a user rather than running it from root.
Sir,
Okay.
I have a question. So
Yes.
can we run sudo block mesh? Might that work?
Let him try. Hopefully, we don't know. I
Can
have
you
not
try?
tried, but looking at the error, I figured that this might be the error. You just try once.
Okay, sir.
Can you
Mohan,
type sudo sudo space the block mesh? Sudo space
Space.
block mesh. No, okay, it's not allowed. So you
Okay.
have to reinstall in the normal folder instead of root.
Okay. I'll try it. Thank you.
so Arun is having a suggestion. Maybe you can try that, Mohan. I think we have not tried that. So create a run directory, maybe in some other location, and then go over there and then try to run. Yeah, that is possible. Thanks, Arun. We can try that.
Okay, sir. I'll do that. Thank you.
Uh, Maybe create a run directory in home, and then copy this folder over there and run the same thing. See if that works.
Okay, sir. I'll check that.
So which case file, the paraview case file or the simulation alone? Because whatever the simulation you have run, it is already saved. In the case directory, you can see the values like 0.01, 0.2. So those are the time steps. Those are the case files actually. So you need not save them separately. Also, I think someone asked how we can plot residuals. So I will try to explain it quickly. Okay, this is the file which we used yesterday for external aerodynamics. In the functions, we had three functions. So the one is force coefficients, which we monitored. The other two are y plus and residuals. So this residual function is a default function, so which we will be giving inside the system. Okay, so either you can place the residual file here itself, or in this case I have made a folder called functions and then kept the force coefficients and residuals inside that. So that location of the functions folder will be in the system directory. So as you can see, I have the 0 constant system files. This is the case directory where we ran the simulation. Inside the system, we have a folder called functions. Inside that, I have placed the residuals. So I will open and show you what is there inside residuals. So it is a very default file which you can copy, paste, and use. You can see what are the values for which you want the residuals. So here I have selected P, U, E, K, omega, and nu t. So I just use a default file. Any standard case comes with the residual file, and you can copy paste. So I have done the same, and we can visualize through one method. The method is, after you run the simulation, you will find a new folder which you did not create called the post processing. So only inside this we found the force coefficients. Inside that we found the coefficients.dat, which we used to plot to see the CDCL graph, right? So similarly, we will be using foam monitor command or GNU plot command to view it. But there is a one small change. If you see in the PPT which was shared to you yesterday for viewing the force coefficients, it will have a command something like foam monitor space -L, and it will start with post processing, and it will say force coefficients and so on. The -L here says logarithmic graph. So the -L will be used for CDCL graph because it is inside a very small scale up to 0 to 2.5. But the residuals we can view without using a logarithmic graph itself. So the command will be foam monitor. Then we will enter into post processing folder, and inside that we will have residuals, then 0 and residuals.dat. So when you hit enter, you can see the file. So actually GNU plot crashes for my system. I don't know why, but it should work for you all. Yeah, it absolutely crashes. So this is the method. That is all I wanted to say. You can plot it with different methods. Like you go to the post processing folder. Inside that you have residuals. Inside that you have residuals.dat. If you open this, you will find all the residual files. Okay, then you can copy paste this or import this file inside Excel or Python or Google Sheets to plot this. So yeah, that's it about plotting residuals. Rishikesh, you are inside the K epsilon folder and not inside RE1 E6. So check your directory. The K epsilon is just a folder. Inside that you have two more folders called RE1E6 and RE20E3, right? So you have to go inside whichever folder where you have the simulation. So before you type any commands related to OpenFOAM, just type ls and see if you are in the right directory. Only then you have to try running commands like block mesh or running simple foam, whatever.
Could you just repeat where we have to use the post-processing command?
Yeah,
In
see,
which directory?
when you are running it,
Yeah.
you are in the directory of K epsilon, right?
Yeah.
So first type cd space whatever Reynolds number you are using, RE1E6 probably, right? So once you enter into that folder, you type ls, you should be able to see the 0 constant and system files.
Yeah, yes.
Yeah, that is the directory where you can run any OpenFOAM command.
Okay, so as all of you have cleared your doubts, so for today we are closing the session here. Thank you and bye-bye everybody. Thanks for joining.